Ice, ice, baby!
If we are interested in the frequency-dependent behavior of a system, such as an electrochemical interface, to observe, for example, how fast or slow related processes occur, we will measure an impedance spectrum. That means we determine the impedance for different frequencies. Impedance spectra are commonly visualized in two plots, Nyquist and Bode plots. As we have seen earlier, the current response to an alternating voltage is characterized by an amplitude and a phase shift. Because the impedance is the function relating current and voltage, it also contains two pieces of information, the relation between amplitudes and the phase shift. So, the Bode plot displays them on two separate y-axes, as they change with frequency. Usually we measure over several orders of magnitude of frequency, and thus use logarithmic scaling. The same applies to the axis of the absolute value of impedance. Both the relation of amplitudes and phase shift can be expressed by a single complex number in the complex plane. If we take, for example, this impedance, we can easily read out its magnitude and its phase shift. Note that we have to use the same scaling for the real and the imaginary axis so that the geometry works out. This complex plane plot for impedance spectra is called Nyquist plot. In the Nyquist plot, negative imaginary part of impedance is plotted against the real part of impedance. A resistor introduces no phase shift and no frequency dependence. Consequently, its impedance spectrum is a point in the Nyquist plot. That means if I measure at different frequencies, I always observe the same impedance for each measurement. In the Bode plot, the magnitude and phase are constant. A capacitor always introduces a -90-degree phase shift, but its magnitude of impedance is inversely proportional to the frequency. In the complex plane of the Nyquist plot, this results in a straight line at a -90-degree angle from the real axis starting at the origin. If resistor and capacitor are connected in series, their impedances add. In the Nyquist plot, the impedance spectrum is a straight line parallel to the imaginary axis. The current always has to flow through the resistor when charging the capacitor. To understand the Bode plot, remember that two impedances are added, where one remains constant and the other is inversely proportional to frequency. For very high frequencies, the impedance of the capacitor will be much lower than that of the resistor, and the spectrum will look almost exactly like that of the resistor. For very low frequencies, the impedance of the resistor will be much lower and the spectrum will resemble that of a capacitor, a linearly falling logarithm of magnitude and a phase angle approaching -90 degrees. At intermediate frequencies, there is a transition.
Welcome back to our video about what is an electrochemical impedance spectrum. The last time we looked at the spectra of a resistor, a capacitor, and both of these elements in series. However, sometimes these are not all the circuits that we need to represent what goes on in an electrochemical system. Sometimes parallel circuits are needed, and this is what we want to look at today. So first, let me introduce you to how the impedance of a parallel circuit is calculated. The parallel circuit is basically the analog of the series circuit, just now it's not the current that is common for both elements, but the voltage that falls off over them. So what you have is generally two impedances, Z1 and Z2. Which are connected in parallel. And what we're looking for is the impedance Z parallel that we can set instead of this parallel circuit and get the same result. And how we calculate this is the known formula. Either we use the reciprocal of the impedances that sum up. So one of the formulas is 1 over Z parallel equals 1 over Z1 plus 1 over Z2. Or, more convenient sometimes, it is to just multiply this equation with Z1, Z2 and Z parallel and reform it, and we will get that Z parallel is equal to Z1 multiplied with Z2 over Z1 plus Z2. Now that we know how to calculate this, let's go on and check our RC parallel circuit. As the name suggests, what we have here, Z1 I now write as a resistor, and Z2 we represent now as a capacitor. And these impedances we are now well familiar with. The impedance of the resistor here is R, and the impedance of the capacitor is 1 or minus J times 1 over omega C. And if we apply this formula, we get for the total impedance of this parallel circuit, I will now apply this formula and name this ZRC. So we multiply these two. And for this, it's actually more convenient for this moment to use the representation of 1 over J omega C. And we multiply them. The impedance of the resistor is Z1 times the impedance of the capacitor, which is 1 over J omega C, divided by the sum. And this equals 1 over, or R over, take this denominator down into the main denominator, and this cancels out, and we get a 1 plus J omega C times R. And we get the final form of the impedance of the RC parallel circuit. Now, since this looks slightly complicated to visualize, and we would like to know what the Nyquist and Bode plots look like, a good technique to approach this is to look at characteristic points, where this calculation gets more simple. And 3 typical points that we would like to look at are where the frequency goes to infinity for very high frequencies, where this approaches 0 for very low frequencies, and where this CR, which we now know as the time constant tau, times omega, which is the speed with which we probe the system, just turn out to be 1. First, let's look at very high frequencies. Omega approaches infinity. This term will become very small, because the omega that gets very large, the denominator tends towards infinity, and this entire term, ZRC, will tend towards 0, because we have a finite value in the numerator and an infinite value in the denominator. So for omega to infinity, ZRC goes towards 0. So let's plot this immediately. We know that for very high frequencies, we're going to end up here, at 0. Now let's check the next value. If we have very low frequencies, omega goes towards 0. And if omega goes towards 0, this imaginary part disappears. J times 0 times CR is just 0. And then what we have is R over 1. Now that's simple, that's R. And that too we are familiar with in the Nyquist plot. I will just put this here. It's obviously on the real axis because it has no imaginary component. And I will put it like this. This here is R. And now the third interesting point where our calculation still remains simple is where omega times CR equals 1. And this means that omega is 1 over CR. And now let's look at what comes out. If this term tends towards 1, we have remaining here r over 1 plus j times 1. And so this, if we simplify this, what we get is we get a real part of r half and an imaginary part of r half. Now, what this turns out to be is a point that is located here at r half on the real axis and minus r half on the imaginary axis, which is this point. If you would like to know more about how to evaluate these terms, I would like to refer you to the seminar tasks that we will have prepared at some point. And as it turns out, if you move across the frequencies and just plot this term, what you get is from high frequencies to the low frequencies a semicircle that goes from 0 to r across this point. In the Bode plot, what this means is that for very, very high frequencies, the magnitude here goes towards 0. It is this falling curve. For very, very high frequencies, the magnitude levels off. For very low frequencies, the magnitude levels off. This makes intuitive sense, because in our parallel circuit, the current has two ways to pass through the circuit. And if we have a resistor and a capacitor, and the capacitor for low frequencies has an infinitely high impedance, then it kind of falls away as a path for a current, so only the resistance remains. Whereas for low frequencies, the impedance of the capacitor gets very, very low, and the current will take the path of least resistance, and only the capacitor will remain as contributing to the total impedance. And so what we get is this behavior for very low frequencies. We level off here, and for very high frequencies it will continuously fall. Likewise, the phase will shift. For the very, very low frequencies, if the capacitor doesn't really contribute because it's just so large, then the phase angle will likewise be 0. And at high frequencies, if the capacitor dominates, then also the phase angle will tend to be what the capacitor is. So what we get is similarly here a shift towards minus 90 degrees. And these are the Nyquist and Bode plots for the RC circuit in parallel. Now a second case we would like to look at is where another resistance, such as for example the solution resistance, is added to this parallel RC circuit. And this slightly modifies the spectra that we expect. I will now rename this series resistance with RS and the parallel resistance SRP to distinguish them. And the impedance of the capacitor remains the same. And it is 1 over j omega Cp. And to calculate the impedance of this circuit, fortunately, we have done all the work already, because as we know, for series connections, the impedance is just add. And we know the impedance of this parallel circuit already. It is expressed here. And all we do is add a series resistance. So the total impedance of ZR RC will be the series resistance plus what we found out here, which is R parallel over 1 plus j omega C R parallel. And now all the same kind of analysis applies again to find out a spectrum. First, let's look at the characteristic point where the frequency tends towards infinity. If the frequency gets very high, again this term tends towards 0, and all that remains is now not 0, but the resistance R. So we will begin not at 0, but already at the offset R series, which is here. And now, for very, very low frequencies, we again have here Rp remaining because this tends towards 0, so we have Rp over 1 plus 0, And what we end up with is R series plus R parallel, which is the sum of the two, which is now not here, but shifted by Rs towards here. And this additional distance is R parallel. And now, in terms of what happens when omega tends towards 1 over CR, we really don't have to rethink this, because this term is just added to the RS, so the same shape will apply. Everything that we have done now is for every single value for the frequencies, we add RS. So we've shifted the half circle, the semicircle, over here. This point for omega equals 1 over CRP will now be here, at a height of RP half, except that we've now shifted it to the right by RS. And now the same semicircle shape emerges. Now imagine that this deformed shape is actually representative of the semicircle. However, in the Bode plot, what is remarkable about this, the Bode plot changes slightly more. Because what we have now for very high frequencies is not this kind of zero path where it goes towards infinity, but for the very, very high frequencies, what we end up with is again a resistor. Because this entire parallel circuit for very high frequencies turns out to tend towards zero, because for high frequencies, the capacitor essentially just lets through all the current without any significant voltage falling off. And so all the current that passes through here is not hindered by the capacitor, but only by the series resistance. And so for high frequencies, we would expect again here a resistance and resistive behavior and a flat plateau where the phase angle is 0 degrees. For very low frequencies, well, we've just found out that for this circuit here, for very low frequencies, we expect a resistive behavior, and all we've added is another resistor, so we will again expect resistive behavior. So of course, everything that changes is that now for very low frequencies, we have R series plus R parallel, but the phase angle stays at 0. And so I should represent this, that this magnitude here is slightly higher, where it's R series plus R parallel. Now, in between, this magnitude falls from one plateau here for low frequencies to the other plateau for high frequencies. But what now happens with the phase angle? So one way to think about what happens to the phase angle is to actually look at the Nyquist plot, which we can more easily construct in this case, and read off the phase angles. So for each point of the impedance here, we know that we can pick this point and plot or find out the phase angle by basically drawing the line to the origin and visualizing the phase angle here. And so what happens is that this phase angle, from starting here at Rs, where it's obviously 0, gets higher, 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 and then lower again. So it makes this kind of bow down to some value here. Let's imagine that it's somewhere between 0 and 90 degrees. It's obviously less than 90 degrees because it never reaches here. But it then turns again towards 0 degrees. So what we have will qualitatively be some shape like this. And exactly where it ends up is a question of the actual values involved. And so these are the shapes of the impedance spectra that we expect if we have an RC circuit or in parallel, or an RC circuit in parallel with a series resistor. Welcome to the lab. Now that we know what we expect from our impedance spectra of an RC parallel circuit with and without a resistor in series, I've built these circuits again here with electronic components, and now we can measure them to see if the spectra match our expectations. First of all, we have here an RC parallel circuit with a 1 mega ohm resistor in parallel with a 10 nanofarad capacitor. And here we have that same 1 mega ohm resistor parallel to 10 nanofarad capacitance in series with a 100 kilo ohm resistor. Now let's wire the first one up, the RC parallel circuit, and see what the spectrum looks like when we measure it. I will now perform a potentiostatic electrochemical impedance spectrum measurement in the frequency range of 50 kHz to 500 mHz and see what the spectrum looks like. As the spectrum begins to form here, you see that for high frequencies we begin on the imaginary axis near the origin. And now with ever lower frequencies, the shape of a semicircle begins to form. You can see that the radius here in the vertical direction on the imaginary axis is 500 kilo ohms, and you can see that the diameter will turn out around 1 mega ohm resistance, which matches exactly the elements that we've used. Let's briefly verify that the Bode plot also matches what we expect of it, and you can see the familiar characteristics where you have a resistor and then the falling magnitude. Let's look at the circuit where we have the additional resistance in series. Okay, let's restart the measurement. As we begin here for high frequencies, we don't start at the origin, but on the real axis with an offset of 100 kilo ohms, which is our series resistance. However, the shape we see now should look very familiar because it's exactly that same semicircle we just measured, just that it's now offset 100 kilo ohms towards higher real part of the impedance. And once more, for very, very low frequencies, we finish down here at 1.1 mega ohms. Looking at the Bode plot, we find that the shape also matches our expectations. You can see here that you see these familiar steps where you have here the 1.1 mega ohms resistance or magnitude of the impedance for the low frequencies, and here only the 100 kilo ohm series resistance for high frequencies, and this downturn in the phase shift where the capacitor becomes relevant.
Hello everyone, my name is Anastasia and I'm a PhD student in SHAPE-EC group, and today I'd like to present you measurements of impedance spectra of ferrocyanide redox couple. And let's start with solutions that I prepared for these measurements. First solution is a conductive salt of 1 molar potassium nitrate, and second solution is include this conductive salt and 40 millimolar of redox couple pair. For these measurements we used this setup that include again electrolyte solution in a beaker, also include working electrode. It's a platinum macro disc electrode. For carbon, for counter electrode we use carbon rod, and for reference we used mercury sulfide electrode. This setup connected with potentiostat, Tsana potentiostat that connected with laptop. Before actual measurements we did impedance spectroscopy of conductive salt without redox pair, and here you can see a typical RC series circuit. It's a linear behavior that are not perfectly parallel to the imaginary part of Nyquist plot because of it's a real non-ideal system. And next we add redox pair that I showed before, and made a cyclical voltammetry of this solution, and we can see that it looks like a typical duck shape. It has a typical duck shape form. And now we want to show you actual measurements of this system, impedance spectroscopy measurements. And here we can start. So we can see a real part of Nyquist plot, imaginary part, and right now we are in high frequency region, and we see how it continuously goes, and it should looks like a semicircle, and we see how it goes and circle. So nice, it's done. And after that I want to change to another concentrate of redox pair to see how it change if we reduce the concentration of ferrocyanide solution. Okay, I changed the solution, and right now we will use a solution with decreased concentration, 40 millimole iron redox pair instead of 60, like we measured before. And let's do this impedance spectroscopy again. Right now here we again see the real part of Nyquist plot and imaginary part. And right now we are again in the high frequency range, and we see how it goes. We decreased the concentration, but again we add redox pair, so we should see this semicircle, but it should be changed, and nice, it's done. So the next step, we decide to compare two semicircles with low concentration and with more bigger concentration. And what we see that with lower concentrations of redox couple, semicircle looks bigger, and with more concentrated solution looks also like a semicircle, but little. Finally, let's look at the body plot of last one measurements. And blue curve is a impedance magnitude over the frequency, and red one, it's a phase angle. We can see that in the low frequency range and high frequency, a magnitude has some kind of plateau, and phase angle reach near zero values, but in the middle part, magnitude decreased, and phase angle has a peak that relates between 0 and 90 degrees.
Hi, welcome back to the whiteboard. So let's see what we can gain from Nastya's experiment in the lab. So what she probed was the ferrocyanide redox couple in solution with a supporting electrolyte. And the impedance spectra she recorded looked like this. So we had the semicircle, which may look familiar to you after our previous video and the scenes we started with. So let's think what electrical equivalent we could find for this electrochemical system, which gave us a semicircle in the complex plane. So as we've seen, the very typical circuit which gives a semicircle is a parallel RC element. So we have a capacitor, and in parallel to that an ohmic resistor. So this might sufficiently model our interfacial behavior for this electrochemical system. But what we have also seen is that for high frequencies, we don't measure an impedance without a real part. So the real part is not zero. We have actually this offset. The semicircle is shifted along the real axis. So that means for frequency independently, we always go through a certain resistance, and we need a resistor which accounts for that in our equivalent circuit picture. So let me draw another resistor here. So if we try to make sense of that, we have to think of where this voltage drop we always observe comes from. So all current we send through our electrochemical interface, and at our electrochemical interface experiences this voltage drop. So we obviously have a resistance here. So what could it be? So the current obviously always flows through contacts, flows through the electrode, and of course the electrolyte. And as we know that the conductivity of our electrolyte is orders of magnitude lower than for a metallic wire, for example, we may easily assume that we have here the electrolyte resistance. And of course, correspondingly then for this ohmic resistor, also an R electrolyte. If I use this later, I will abbreviate it just with REL. So, and this is obviously a frequency-independent resistance. We always see in the current, so in the Nyquist plot, it would relate to this section here. So this already tells us also about first uses where electrochemical impedance spectroscopy can be actually applied. So for example, we might be interested in the electrolyte conductivity of an unknown system. So what we could do is have our electrochemical cell where we can measure the impedance and use certain solutions where we know the conductivity already. So we could do kind of a calibration with this known solutions of known conductivity, and then measure the unknown solution and relate our measured ohmic resistance here in the high frequency part of the impedance spectrum to the electrolyte conductivity. Another case we often encounter in electrocatalysis. Here electrocatalysts are often researched regarding their electron charge transfer kinetics for the electrocatalytic process, and this is done by linear sweep voltammetry. For this, the potential is swept and the current is measured, but here also the current always has to flow through the electrolyte. But this is not what we want to characterize. We are interested in the interface. So we want to compensate for this ohmic drop we experience here. To do that, there are different methods, but they all require that we actually determine the ohmic drop first, and impedance spectroscopy is a helpful tool for this. So we made it through this part. Now let's look at our actual interfacial behavior. So here we had a capacitor in the electrical circuit to get this feature of the semicircle. In our electrochemical system, this is most likely the double layer capacitance. So let's think about if we could somehow get this from our measured impedance spectrum. To do this, we remember the formula of the impedance for a parallel RC circuit. So RC circuit, parallel, as this section here drawn, and this is, as we know, a frequency-dependent value. So we have our general formula for the parallel RC circuit here, and as we have seen, we often can already gain a lot from this if we look at the value of the impedance for specific frequencies. So let's see here what we get for this impedance if we consider the inverse time constant, 1 over RC, as characteristic frequency. So we basically lose this term. And now if we expand the equation we get with the complex conjugate, we arrive to this term. As we can see, it's quite easy to separate this into real and imaginary part. So, considering this parallel RC circuit, I write here just R for now for the resistor, we know that this is the diameter of the semicircle. Because if we go to very low frequencies, if the angular frequency approaches 0, the current will flow through these two resistors. So separating our electrolyte, we here have the diameter of the semicircle, like on the real axis, as the resistance. So if we know that, we can see that we have the specific point here for half of the resistance in the real part and half in the imaginary part. So where we arrive to is the vertex of the semicircle, and this we can easily read off from our impedance spectrum. And if we now rearrange this term for the capacitance, we see that we arrived to a simple way to determine our double layer capacitance just from the impedance spectrum of our redox pair. So we found an interpretation for our ohmic resistor as electrolyte resistance, and we learned how we could calculate the double layer capacitance of our system in this easy case. So what can we learn from this resistor? Generally speaking, the resistance is the linear relation of the voltage drop across the resistor and the current flowing through. For our interfacial current, we have two contributions. We considered already here the double layer charging. So what is left is the charge transfer through the interface, which is related to our electrochemical redox reaction. So let me name this resistance charge transfer resistance. And this applies then also here with the abbreviation CT. Here I had my double layer capacitance actually, and here that would be also RCT and C double layer. You get the principle. So let's try to assign some extra chemical meaning to that. So in our case, we were at the equilibrium potential. And we will now ask ourselves, what are the electrochemical reactions we have under these conditions? So we have our interface with electrode, I draw here on the left side, and the electrolyte containing the redox pair, I draw on the right side. So we here, for example, have the iron 2 species, which can be oxidized to the iron 3 species. Then we have electrons, which have to go through the interface, and we have an anodic current. Furthermore, we have of course also the iron 3 species, which can be reduced to the iron 2 species. And accordingly, we have a cathodic current flowing at the very same interface. So equilibrium potential here means that we actually don't observe a net current flow, but it still means we can have partial currents and therefore also a charge transfer resistance we can characterize by our impedance spectroscopy. Let me make some graphical explanation which emphasizes this idea. So if we consider how the current relates to potential changes. I can draw here a diagram with a potential axis and a current axis. And my point here, this is the equilibrium potential. So if I look now at the anodic current, I can draw, for example, something like this. This is my anodic current. And at the cathodic branch, I see equally an exponential relation. And now I can also see what equilibrium potential and this electrochemical equilibrium here means, because I see that at this potential the anodic and the cathodic current cancel out, so they have the same absolute value. So here at my equilibrium potential, and this is called actually exchange current in electrochemistry. So now let us look at the sum current to see what happens. So I can see if I go very far away with the potential from my equilibrium potential, I approach to having only the anodic current. And similarly, I also see that for the net current when I go here to the cathodic branch. And again, my net current being 0 at the equilibrium potential. Actually, this higher or lower potentials I can also refer to as overpotential. And then here at the equilibrium, that would mean my overpotential is 0. If I would have a higher exchange current density, that means I need only very small overpotentials to fastly arrive to much higher currents. If I would have a very low exchange current density, you can imagine that I need already quite big steps to achieve a bit of higher current. And if I consider my example here, which is a single electron transfer, and we had equal concentrations of the iron 2 and the iron 3 species, and I also assume that the transfer coefficient is actually 0.5, I can also write an easy equation for my exchange current, which would relate it to the Faraday constant, so charge per mole, and the surface area, so how much sites do I have where I can channel electrons through, the heterogeneous rate constant, and the concentration of my redox species. So you can see that the exchange current density is kind of an expression in electrochemistry for even that, this heterogeneous rate constant, just making a current out of it, which is more familiar for us because we can actually measure it. So having done that, I can also put this, what I picturized here for you, into mathematical expressions. What I would use here to describe this relation of current and overpotential is the Butler-Volmer formalism. So here I want to express my current, which needs this exchange current density, which characterizes the process via its heterogeneous rate constant, and this exponential multiplies it with these exponential expressions. As I apply only very small perturbations in my electrochemical impedance spectroscopy experiment, so here around the equilibrium potential, only about here, I can actually try to linearize this expression. Therefore, I use a Taylor expansion, which I stop after the second term. This simplifies this exponential function actually to x plus 1. Meaning that I here then get just my exchange current, the constants, Faraday constant, gas constant and temperature, which is not constant, but I keep it constant in the experiment, and the overpotential. And now I can actually simply derive an expression which has the dimension of a resistance by rearranging the term. So I have my charge transfer resistance for the equilibrium potential, which I define now as the negative of the overpotential to the current. And see that I can actually relate this specific charge transfer resistance, which I developed around the equilibrium potential, with the exchange current. So by this I can get meaningful measures out of my electrochemical impedance experiment. What is quite remarkable about this example we have chosen with the iron 2 iron 3 redox pair is that it actually is electrochemical reversible. That means in the scan rate ranges we would use to conduct the cyclic voltammetry, you have also seen in Nastia's experiment, we would not be able to observe this current potential relation because we have a very fast kinetics. So that means here we kind of arrive to something like this, where then this very fast kinetics, so establishing very fastly the electrochemical equilibrium as soon as we change the overpotential, means that we have just a change of the concentration ratio, and therefore the current potential relation does not follow this Butler-Vollmer formalism, but is described by Nernstian behavior. So that means from this part of the cyclic voltammogram where the current is rising with the potential before the peak, you cannot estimate any kinetics. But with our electrochemical impedance experiment, we were able to measure easily in such high frequency ranges that we could separate those processes and have for this very fast kinetics even quite well separated from the mass transfer behavior, our semicircle we can easily describe. So if we remember what we've seen for the lower concentration, we can now easily understand why we arrived to a bigger semicircle with a higher charge transfer resistance. That was just because we affected the exchange current by altering the concentration. As we reached our season final, we will summarize today's episode just now. First, we looked at what happens if we combine a capacitor and a resistor in parallel. To sketch and understand the impedance spectrum, we make our life easier by looking at certain frequencies where the calculation simplifies. Towards infinite angular frequency, the magnitude of the impedance approaches 0, and the phase angle approaches minus 90 degrees. For an angular frequency of 0, that is direct voltage, the impedance simplifies to the resistance with no imaginary part. The phase angle is 0 degrees. In between, there is a point where angular frequency times RC is just 1, which we will call characteristic angular frequency for now. Here we find the top of the semicircle. This point allows us to calculate the capacitance easily, as the resistance can be read off as the diameter of the semicircle on the real axis. Moving on to the electrochemical impedance spectra, we recorded the EIS of a ferriferrous cyanide redox couple in solution and obtained semicircles which were shifted along the real axis. So here we can find an electrical circuit which behaves similarly, our first equivalent circuit for an electrochemical reaction. When we apply a small potential perturbation to the electrochemical cell, all related current must necessarily flow through the electrolyte. For this reason, we have an ohmic contribution to the electrolyte resistance. At the interface, the current has two pathways available. On the one hand, it can rearrange the electrochemical double layer, and on the other hand, electrons can be transferred through the interface, oxidizing or reducing an electrolyte species. So we can use the parallel RC circuit with an additional resistor in series to model the system. The impedances add. In the Nyquist plot, adding a frequency-independent resistance results in a shift of the semicircle. In the Bode plot, the low-frequency behavior is similar as electrolyte and charge transfer resistance add. For high frequencies, the magnitude tends towards the electrolyte resistance as the capacitor bypasses the charge transfer resistance. Correspondingly, the phase does not tend towards -90 degrees for high frequencies, but goes through an intermediate shift before returning to 0 degrees. Now that we can quantify these equivalent electrical components, what do they tell us about our electrochemical system? Determining the double layer capacitance, for example, could help us to assess the electrochemically active surface area. If we consider the electrolyte resistance, it may relate to the section between the working and the counter electrode for a 2-electrode setup, or the section between the reference and the working electrode for a 3-electrode configuration. In the latter case, we often choose this experimental approach to apply potentials precisely to the interface. So we are interested then in determining this ohmic drop due to the electrolyte resistance in order to compensate for it in other measurements. We can also use impedance spectroscopy to obtain important properties of chemical systems, such as heterogeneous rate constants. For this, we derive relationships for potential and current based on electrochemical models and theories and compare them to mathematical descriptions of our electrical analogy. For example, how much current flows at a given electrode potential can be described by Butler-Vollmer kinetics. While this is an exponential relation for small perturbations as we apply during EIS, we may accurately linearize this equation and model it with a resistor. Under special conditions, we can calculate the exchange current density from this resistance, and we may use this to infer the standard heterogeneous rate constant. We must take special care that all the conditions and assumptions we made are fulfilled, because only then our equation is valid.